So to do this, you need to be able to draw some right angles, and you also need to have some uniform measurements, same distance vertical, same distance horizontal. So a couple ways you can do that. You could have a piece of graph paper like I happen to have here on the screen, or maybe a real piece of paper, graph paper. If you happen to have a printer, you could print yourself some graph paper. I have a link here to dot paper. So there's this online company called Incompetech, kind of a weird name. They have lots of weird ads, which I just ignore, but I can create dot paper here. They have some default settings that you could play around with, and then after you play with those, you just hit download PDF, and it saves a file, in this case called square dots. And if I open up that file, what I'll see is an 8.5 by 11 piece of paper with equally spaced dots vertically and horizontally. So those dots look kind of faint. So if we weren't happy with that, we could always do something like make them black and then make the point a little bigger, like size 2. This says 2 dots per inch. Maybe you like centimeters better. So maybe I could do 1 dot every centimeter. So this can be a slightly different one. We'll call it square dots, centimeters. So now the spacing is a little bit different. Instead of every 1/2 inch on the other one I had, that's this one here. If I printed this out, this is an 8.5 by 11 paper. They're now every centimeter apart. So this is a nice place to draw if you have trouble drawing neatly, which I do often. Other thing we could do is I have this Geo Board app linked here. So this gives me this nicely spaced, and by the way, a Geo Board is a pegboard, and then we use elastics on that pegboard by plopping the elastic on a point, stretching the elastic out, and sticking it to other points. So I can make myself a triangle by playing around. And if you grab the circles that are made, that moves, and you can only land on a peg. So if we were in the classroom today, I would have these wooden boards or these plastic boards with these pegs sticking up and a whole bunch of elastics, and we'd be flinging elastics around the room. Fortunately, we don't get to do that. We just get these fake elastics. And you can put more than one of them on there at a time. So I can put another one here. And if you grab the middle of it, that allows you to create a new point. So my blue triangle has a height of 3 and a base of 3. My orange triangle has a height of 1, 2, 3 and a base of 3, but they look a little bit different. So the goal here is we're going to make some triangles, and we're going to try and measure their areas and their perimeters. Mostly I care about the perimeter because that's where the Pythagorean theorem comes in. So in the activity here, I give an example. I made a triangle. Ooh, I lied. It says I got some mixed up stuff here. I started off with a base of 2 and a height of 3, and then I changed my mind. So I'll clean that up and fix it in a second. But I'll walk through this example and then I'll clean it up. I want you to make some down here with a base of 2 and a height of 3 on a Geo Board or graph paper or that dot paper, however you choose. So I'll do it in a couple of different ways. So let me fix this example, but on my Geo Board here. And then I'll do it on regular paper. So let's see, my Zoom screen's in the way. Can I just trash everything? Click trash. So this particular app is by that Math Learning Center. We've been playing with their apps before. I can get a bigger Geo Board. I can also get a circular Geo Board to play with. So I just want to use the little Geo Board because we're just going to play with little triangles here. Any color you want is fine, so I feel like green today. So I'm going to make a triangle with a height of 3 and a base of 1. And then I want to find its perimeter and its area. So perimeter, part of that's pretty easy. Well, I can see across the bottom, there's 1 unit on the bottom. 1, 2, 3, so for sure there's 4 in this part of the perimeter, but I got to figure out what this diagonal is. And for example, if I go straight up to this point, that would be 1. So the diagonal to here is going to be a little more than 1, another a little bit more than 1, and another a little bit more than 1. So this right here is going to be a bit more than 3 altogether. How much more than 3? Well, we're going to have to calculate that. So I have, and I'll do a non-right triangle too in a sec. So I happen to have a right triangle, a base of 1, and a height of 3. And I'll give you another example of why I'm using the Geo Board for this in a minute, but for now it doesn't matter too much. So let's suppose here I blow it up a little bit and I let every 3 is going to be 1. So that'd be 1 pair of dots, and then I have to go up 3. Things need to be equidistant. All right, so I'm trying to mimic my Geo Board here on paper. Oops, kind of ran out of room that way. So then the triangle I was trying to make had a base of 1 here and a height of 3. And now, if I want the perimeter, I need to know what that diagonal is. And remember that this is a right triangle, so that's a right angle. So I want the perimeter. And I can see here the perimeter is 1 plus 3 plus whatever that diagonal is. So let's call it D for diagonal. That's a 1. That's a 3. Pythagorean theorem helps me out here. Pythagorean theorem says that 1 squared plus 3 squared has to be equal to the diagonal squared. 1 squared is 1, 3 squared is 9, that's 10. So I'm trying to find a number whose square is 10. Well, that's what the square root means. What number has a square of 10? This number. Now, 10 is not a perfect square, so that is the exact answer. And so what I'd like you to find is the exact answer. If I plug this into a calculator, I no longer have an exact answer. So for example, if I go to my calculator, choose Desmos, and I say, hey calculator, what's the square root of 10? Calculator gives me an answer. 3.16227766. Looks like it might be, hey, there might be a repeat going on there. But if we plug it into a calculator with more decimals, we're going to see, damn, it doesn't repeat. So let's suppose I go with that version of the number, 16227766. Lost track of it one more time. 16227766. Now, my calculator stopped there, so that must be the whole answer. Now, the problem with that is this is actually a fraction here, right? Tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, millions, 10 millions, 100 millions, right? So I could write that as 3 and 162277766 over 100000000. And the square root of 10, since 10 is not a perfect square, can't be a fraction. So this number right here, whether right it's a decimal or a fraction, is not an exact answer. No matter how many decimal places I go, it's an approximate. So the best I can say, it's not equal, it's approximate. And I would like you to find exact answers. So as far as the diagonal here, I now know that that's the square root of 10, so the perimeter is 1 plus 3 plus the square root of 10. Well, 1 plus 3, that's easy, that's 4. But there's really not much I can do about the square root of 10, so this is the only way to write the exact answer. That is the exact perimeter. So I want you to come up with the exact perimeter. So generally, 2 of the numbers we can add, and 1 of the numbers we can't. Let's try another one. Oh, area, by the way, you should notice here that this triangle sits inside of a rectangle. That rectangle is 1 by 3. So the rectangle has an area of 3 square units. That diagonal cuts it in half. So the area of this triangle would be 1 times 3, cut it in half, 3 halves as a fraction, or 1.5. All right, let's try another one. And I do have these questions, and then I'll let you guys play for a little bit before we're done. Geo Board. So I'm going to make another 1 by 3, and I'm just going to do that by moving this top point. Now that's really the same triangle. It's just a mirror image of it. So that's not a different 1 by 3 triangle. I got to move this way over to get a different triangle. All right, so there's my different one right there. It has 1 as the base, and from the base, the point is 1, 2, 3 units up. So this triangle has a base of 1 and a height of 3. So I'm going to redraw that on my paper. I want to find out what's the perimeter and what's the area of that triangle. So now I have this other triangle. It's not a right triangle. Base of 1 and a height of 3. So I'm going to put some dots on my graph paper to draw that out. How far over did I go? I think I just went 1 unit over. Yep. So making another row of dots, equidistant in a grid. So then my triangle has this for the base right there, and then I made the top over there, so it looks like that. Now here, I have a bit of a conundrum because for sure I know this down here is 1, but these other sides are all longer than 3. So if I go straight up, the distance is 3, right? 1, 2, 3. And that height is perpendicular. So there's my height of 3. But this is a diagonal, so that's going to be longer than 3. That one's going to be longer than 3 right there. So I got to figure those guys out. Well, it turns out I already figured out this length right here in the previous problem, because that is part of a right triangle with a base of 1 and a height of 3. And the Pythagorean theorem on the previous page told me that, hey, if a base of a right triangle is 1 and the height is 3, then the diagonal has to be the square root of 10. So cool, I already did that one. I don't have to repeat that. So I know that this side right here is, teach red, the square root of 10. Now this other side, I got to figure that one out. So let's see. Let's highlight it in yellow. I want to know what this diagonal is right there. Well, that diagonal right there, if I drop straight down, it comes from a height of 3 but a base of 2. So let's find the yellow diagonal. So this one right here comes from a base of 2 squared, a height of 3 squared. It will tell me what it is. So let's call it d squared. So this is my d there. So 2 squared is 4, 3 squared is 9, 4 plus 9 is 13. So what number squared is 13? The answer is the square root of 3. 13, sorry. Because the square root says what number squared is 13. So now I know this side is square root of 13. So the perimeter of this one is 1 plus the square root of 10, that right side diagonal, plus the square root of 13 on the left. And the square root of 10 is really not like the square root of 13, even though they're irrational. I can't really do anything about that addition. So this right there is the perimeter. What about the area of this? Well, there's 2 ways to think about the area. And I'm going to redraw that to kind of figure that out. The first way is to just know a formula. Does anybody know a formula for the area of a triangle? Yeah, base times height divided by 2. Cool. And I can look at this triangle and I can see, oh, the base is 1, the height is 3, so its area must be 1 times 3 divided by 2, which is 3/2, or 1.5. Now, that's kind of interesting because back here I had this other triangle up here a minute ago, and it looked a little different. It looked, maybe I won't use yellow, let's change that to red. So here's my other one. It had a base of 1 and a height of 3, and its area was 1.5. The green one has a base of 1 and a height of 3. Its area is 1.5. And if I throw a purple one in here with the same base, but I put the height way over here, that top point, its baseline is right here. And above that baseline, 1, 2, 3, guess what the area of this purple triangle is? But
1.5.
It's 1.52. Yeah, so I'm just going to show in another way that green triangle has an area of 1.5. And just using right triangles. So I'm just going to draw that back in here. Green. So my green triangle down here, something like that. Now, it's not a right triangle, but I can build some right triangles around this by doing the following. So between these horizontal and vertical red lines and that diagonal, there's a right triangle living up here, and then there's another right triangle living down here in the corner. And all three of these triangles make a rectangle. So this rectangle is 2 by 6. So the total area I've enclosed there is 12. Now, I would like to remove the red one and the other red one, so all I have left is the green one. So what I want to do next is say, okay, well, can I find the area of this red triangle right here? Well, it's a right triangle, and for sure in a right triangle, area is 1/2 base times height. So if I cut off that right triangle there, then I'm certainly cutting off, removing that 1 times 3 over 2, or 1.5. And that's going to leave me, what, 10.5 for the rest of it. And then I've got this other one sitting over here that I would like to remove too, so I can leave the green one behind. And it is half of this whole rectangle, right? It goes from corner to corner there. And if the whole rectangle is 6, that one must be, if the whole thing is 12, that triangle right there must have an area of 6, right? Because it's half of the whole thing. So if I take 6 away from this, oh shit. Somebody needs to point out when I screw stuff up. How tall is this rectangle here?
It's 2 by 3.
It's 2 by 3. Yeah, I got ahead of myself somehow. Put down the answer and then remultiplied it. All right, 2 times 3 is 6. Take away that 1.5. That leaves me with 4.5, right? Yep. And then this bigger triangle up here is half of the whole thing, so it must be a 3. So if we take away 3, the only thing left is the green triangle, which must be an area of 1.5. So even if I only believe areas of triangles that 1/2 base times height applies to right triangles, I can still kind of play around and come up with the area. But we got a formula. Base times height over 2. Height over 2 is the area. So interestingly, there's a lot of triangles who have areas that are rational, but perimeters that are irrational. And a lot of diagonals end up being irrational. Are all diagonals irrational? The answer is no, because we saw this 3, 4, 5 triangle right here, right? 3, right, 4, 5. No irrational numbers here, all rational. So your goal on this activity is to just kind of play around. Instead of 1 by 3 triangles, let's delete some stuff, you're going to make some 2 by 3 triangles. And on those 2 by 3 triangles, and by 2 by 3 I mean base of 2, height of 3, you're going to come up with their perimeters and areas. So the easiest one, does not look there, would be that one. That would be another one. This is really the same mirror image of the first one. It's really not different. So 1, 2, 3. So those could be your 3 different triangles that you make, but there are other options out there. So you're going to draw out 3 different triangles, clearly show they have a base of 2 and a height of 3, find their perimeter and their area. For the perimeter, you'll need the Pythagorean theorem. So that's kind of like the examples I just did. Pretty straightforward, not much of a big deal. Leave the square roots there. The second one's a little more challenging. You got to be creative, and this is going to take a few tries to get it right. I want you to make a triangle here with a perimeter of 12 centimeters. Exactly 12. Exactly 12. There's a bunch of different ways to do it. One is easier than all the others, but I just want you to kind of play around with that and come up with it. So that's going to be part of your homework there. I said I would get to Allie's question, and we're running out of time, so let's do that.
Could I say something real fast, Gary, just as a observation? So the classroom that I work in, when we work in the 4, 5, 6 grades, the kids seem to be they do not like the base times height divided by 2. It throws a lot of the kids. They like the area as base times height times 1/2. For some reason, that's easier for a lot of them to digest the triangle area.
We'll talk more about that next quarter when we do the geometry, but that's a really good point. Like we know that dividing by 2 is the same as multiplying by 1/2 in terms of the whole reciprocal idea. So there are multiple versions of this. So some people write it as 1/2 times the base times the height. I wrote it here as base times height over 2. Sometimes it's written as base times height and then times 1/2. So there's a bunch of different variations of it out there. And yeah, there are pros and cons to all of them, but it's interesting that you say the kids you've been working with like this version right here.
Yeah, they seem to, I don't know, they seem to be able to calculate better, and they don't get so flustered at the fact that they don't have to divide it by 2. Just multiplying it by 1/2 seems easier. So.
Okay, cool, good to know. Thank you for that.